To start off with a little bit about who we are, I'm one of the leaders in the data science and analytics team at Baker Hughes.
My name is Alex Jankolski. I'm a principal architect for data science and analytics at Baker Hughes, a GE company. And we also have Arun on the slide. He's the person who inspired us to do everything that we're going to show you today.
Yeah, so let's get into it. A little bit about our business and our challenges and actually how that gets us some opportunities. When we talk about the oil and gas industry and the energy business, we're talking about an industry that runs on an aging fleet of assets. Not usually those are running at their optimal condition. And that might be because of when or how they were commissioned several years ago. Attached to that, the fact that a downtime in the oil and gas industry is very costly. You really don't want to have a platform like the one shown on the screen go down in production because that can cost you tens of millions of dollars a day in lost production. So you attach to that the fact that the industry is ripe for digitalization and can leverage a lot of what we build as AI and machine learning for predictive maintenance or asset optimization, and you get large opportunities to deploy orchestrated analytics at scale. But what is the data that's going to fuel all of this digitalization? So I come from the renewables industry, actually, and there's a very stark difference between this oil and gas data-rich industry and what I was used to. I could literally fit in one single flash drive, 64 gigabytes, a whole year's worth of operation data from a mid-sized wind farm. And here, one platform like that, it's going to generate terabytes of data every day from tens of thousands of sensors that are recording every second and putting that data down into a historian. Just as a comparison to a usual transactional database, that gets you about 10 or 100x more volume in data recorded. So when we talk about predictive maintenance, when we talked about applying AI and machine learning to these opportunities, every time we try to find one of those events or malfunctions that will lead to a downtime, it's like trying to find a needle not in a haystack, but in an ocean. It's something that you shouldn't be having every day, so it's something that is not there for you to necessarily model easily. So how do we do this? How do we go about understanding and orchestrating analytics for the oil and gas industry? So I want to give you guys a sense of what is the playing field for us in oil and gas. So we are built on an industry that it's built on top of legacy systems, right? So that gravitates you towards a lot of silos of different things, meaning silos of data, meaning silos of code and analytics, meaning silos of even runtime, OSs, everything disparate and separate. So first thing we need to do is actually to tackle unifying that. So for us to put all of it into a single roof, we come up with this unified catalog that tries to contextualize all the dependencies between those heterogeneous types, so we can actually get logic around the analytics that we're going to put forward for our customers. So then when we have this catalog that contextualizes what a model should be modeling, what a data represents, we can build and connect those and create an orchestration. That's what we're going to deploy, and that's what we're going to be talking about today. So these orchestrations are what we call analytics orchestrations. And right now, for me, it's, I guess, good for describing what analytics means to us. Analytics actually means the realization, the end-to-end realization from data to a key performance indicator of business metrics that are going to drive some insights to our customers. Meaning, we're going to get your data, we're going to get the proper model that represents your system, and put forward the information that you're looking for. These orchestrations would normally connect old DLLs, modern Python code, even Golang, and push the results into a deployment where our users can interact. Now, once you have this deployment, you can actually observe what your users are doing with both the analytics, the data, the results. And that's what we leverage to learn and inform back the semantics of our catalog. So this is the first time this is the first loop that I'm going to be showing you today. And you're going to see that over the talk, I'm going to talk a lot about loops. And just to put a side note here, for us, orchestrating analytics, orchestrating AI, it's basically a non-DAG process. There are loops, there are cycles you have to learn every time you have something running. So let's talk about analytics in a usual data science type workflow. If you go and talk to a data scientist, you can try to zone in into an application that is very linear, but would represent the usual atomic level of their work, which is getting a data set, pre-processing the data set into something that they can feed into a heavy compute, machine learning, AI, deep learning-based model, then post-process those results and put forward that metric into a database, put forward that metric into a dashboard, or serve it to the customers. But if you actually try to analyze what's going on, an orchestration looks a little bit more like that. And you can think about that linear workflow like the solid lines in this flow here, in this orchestration, which start with data validation, actually doing some EDA, maybe identifying the points of data that you're actually going to use to build models, what models you're going to build, and then you go into the heavy compute costly piece of the workflow, which is where you train your models and you keep iterating that until you get the best model, your optimal model. That's where you see sleepless nights and several days spent by a coffee field data scientist just trying to get the best model out. Once that model is out, maybe you're going to attach at the end of it, the post-processing phase, another ML workload. You may classify something. You may forecast something. Or you're just going to use heuristics to detect an anomaly, for instance, in a predictive maintenance use case. And once you tune that detectability, once you tune that classification, you can deploy your metric. Now, if you're very lucky, maybe you get user feedback. And that's where you start iterating over your cycles and your loops. So you get user feedback, you retune your detectability, and you're good to go. If you're not that lucky, maybe you need to retrain a little bit pieces of your model. So you go one step back, maybe use transfer learning and update parts of your deep learning model. And if you're not lucky at all, you go all the way back and have to basically build a new model. Try going and telling the data scientist that spent weeks on end that model was not great, and we're going to have to start all over again. It's kind of complicated. But sometimes happens. So that's the reason why at Baker we started looking into ways to automate this workflow and give the data science a more repeatable and scalable way to build those models. So when we tackle a platform like the one I showed before, we can build several models in parallel instead of every time building one model and then 2 weeks later starting the next one. That doesn't scale. So let me talk about that first loop that we saw about training models. So we've, at Baker Hughes, came up with this probabilistic evolutionary framework of optimizing architectures of deep learning models. So when we go about building TensorFlow-based models to detect anomaly, for instance, we don't want to just go and randomly search all the space available and just go and try to tune the hyperparameters. We want to make sure we found our global best model over parameter combinations, over architecture combinations. And for that, what we do is once we build the model and we explore intelligently a space, we build a meta model of the model's performance, and then we apply evolutionary methods to that meta model, which is cheaper to compute. So you start with red dots, which are actually heavy GPU, costly compute. Then you create your meta model, and you apply the evolutionary methods, and then you just go and burst these gray dots and try to find the optimal. If you keep doing that, if you keep iterating, if you keep the cycle, you go from black to blue to red to green, where you get the minimum of both of your objectives or more than 2 objectives. This gives us a 10x improvement over just a random trial and error search. And we end up actually exploring 250,000 architectures. And this is a pretty beefy models space. Now, if you think that that is done by custom scripts, that is also not scalable. So for that, we use a very nice tool from Google called Kubeflow, which gives me a way to Pythonically describe that orchestration. So I can use Python objects to define the operations that are going to give me the initial samples, then the operation that is going to give me the next best models through a genetic algorithm, for instance, and the next few points I'm sampling, and I keep doing that. And that's what you're seeing on the screen. So the first line is actually 120 deep learning models being built concurrently on a Kubernetes cluster. And here we have to be intelligent about using GPUs, because a single GPU is very expensive. Imagine having to have 120. So we can sometimes have split sessions and run 2 or 3 models per GPU. And that's what we do here. We go back in, we optimize, find the better points, and keep doing that until we find the best model. But still, GPU are very expensive. So for that, we try to leverage auto-scaling applications so that every time we need an extra GPU, every time we hit 80, 90% of utilization of our GPU in our clusters, we give it another GPU. And we keep scaling up until the point where we finish up the experiments, we finish up the loops. And here you see on the bottom right-hand corner that we start with a baseline that's probably supporting other GPU workloads. And as this optimization starts, we climb, and then we get them down while we're just running the genetic algorithm. And we keep doing that until we shut them all down. This gets us to a level of automation of building deep learning-based models that can help our customers now, in a reasonable time frame, achieve those AI-based predictive maintenance outcomes that they need. Now, this is not what scale is all about. And I'll leave it up to Alex, my colleague, to dig a little bit deeper into what scale means.
Thank you, Fabio. And hi, everyone. I'm really excited to have this opportunity to talk to you about scale today. In my talk, I will use some analogies, and I invite you to keep an open mind and have fun. So our challenge with scale, to make everything that Fabio just talked about operate at really large scale, put in one word, was just to be smart about it. So we needed to support that typical workflow that Fabio showed, that allows us to continue and not disrupt the productivity and the process that data scientists are already used to. We needed to maintain freedom of choice, because there's a huge diversity of technologies that have accumulated in the oil and gas industry over the past 30 years. And we have to be able to support all of them. We need to keep things simple to ensure adoption of the platforms we're building. We have to be able to readily package and deploy to multiple targets, including on-prem, data centers, and cloud. And we have to run all of this at scale, be able to extract insights and prove the value of these platforms. So we made some choices while building our platforms. And the 3 major ones are, first, run everything in containers. We tell our data scientists, you can do anything that you need to do, use the tools that you're used to, the technologies that help you get to your result. But to productize the fruits of your work, just put everything in a container. And that is why we built the Depend on Docker project, which makes it easy for anyone, even people who are not familiar with Docker, to put their software in a container, be it Linux or Windows. The second choice we made is keep compute and storage completely separate. That gives us very nice flexibility, ease of deployment, and treating the compute as something that's ephemeral. Even if it goes completely away, we can easily stand it back up and bring the systems online. It also allows us to scale. And the third choice is to orchestrate all of these containers using Kubernetes. Today, we're going to see a demo. And for the purposes of this demo, we'll look at this use case. We'll start with a data file that has 20 variables. And that is really a collection of 20 time series. So the answer that we'll be looking for is, what is the very best model that you can build using this data set? Each one of these variables can be the output variable, and each one of the rest of the variables can be used to predict that output variable. So we'll go through this workflow to generate a large number of model building jobs to produce possible models that can be built with that data set. And just for one file that has 20 variables, when all the combinations are put together, and we're also using different modeling techniques. So here, we're going to use 6 different modeling techniques. So for 20 variables, with 6 modeling techniques, you get 120 models that you can build. To show scale, we're also going to simulate 10 users using 10 of these data files simultaneously, producing a total of 1,200 models. And that is a very, very small use case for us. To show you a little bit about the architecture we've put together to help us do that, we basically have 3 layers: a storage layer, a layer with core services, and the runtimes. So for the core services, there is one thing that I want to point out. One of the lessons learned when we were working on scaling this up is that it is necessary to break down the services from generalized services to specialized services. So each individual microservice can scale better. So in the beginning, we had a generic task service, and that got split into several components of that task service, which is the first one responsible for watching the Kubernetes API, the next one responsible for creating model jobs, the next one responsible for collecting the results from jobs that have completed, the last one responsible for cleaning up after everybody. So I can take the whole time of this talk just going over the points in this slide. But I like doing things a lot more than talking about them. So we're just going to hit the high points. Lessons we've learned from this exercise. Large scale doesn't come out of the box. You will be required to work for it. And it's not a manual thing. If you try to repeat and do everything manually, you'll get very tired pretty quickly, and you'll start making significant mistakes. So automation and scripting are key. We already talked about breaking down services to microservices. Monolith services don't lend themselves to scale. And when you're talking about large scale, 100x, you have to be prepared to redesign and rethink what you're doing and maybe rewrite several times. The debate between cloud-managed and self-managed Kubernetes. I'm not going to go too much into that, but all I want to say is that using GKE can save you a lot of sleep. There is this one really useful Kubernetes API called the Watch API, which lets you monitor the status of your pods and get real-time events as changes happen in your cluster. So we're making use of that in our demo. Also, we had made an assumption that it is enough to, hey, just scale my service in Kubernetes, and then traffic will be distributed evenly, and all the pods will be happy to handle an equal amount of traffic. That is not the case. You actually have to do some work to get proper load balancing in Kubernetes. We were seeing that some of our pods were getting so much traffic, they were literally killed and had to restart, and others were just sitting there. So using Envoy proxy solved that problem. Using the Google native cloud load balancer solved that problem. I want to caution you, watch out for the less is more paradox. So in our desire to scale everything so high, we said, all right, let's run 100 of this service and 1,000 of that service and 2,000 of that one. We even scaled one up to 8,000. And things actually slowed down instead of giving us better results. So you really have to think and optimize for what is good for your system and realize that sometimes less is more. Last lesson I learned that will actually bring me back to the next slide is sometimes one Kubernetes cluster is not enough to accomplish what you're trying to do. So when that's the case, just use many. So for the purposes of today's demo, we have built for you a cluster of Kubernetes clusters. What you see here is our master Kubernetes cluster that has all of the services that I showed you in the previous slide scaled up. And this in itself gives you a scalable system because you can scale horizontally by running more nodes in your cluster. You can scale vertically by running larger nodes in your cluster. But what we've done gives you another degree of freedom because you can run as many Kubernetes clusters as you want to handle your load. So now you can spread your system really wide. And by the way, remember how I talked about self-managed versus GKE? Here, we have done both. So it is not required. We can run all of our workloads on GKE or all of them on Kubernetes. But we're going to show you both just because we can. So this is an example of one of our GKE clusters. It has 100 nodes, and it's ready for us to run workloads on. I'm going to zoom out a little bit. These are 5 GKE clusters. So remember how I said I'll make some analogies? What does this remind you of? Let me zoom out one more time. On the top live 5 GKE clusters. In the middle is our management cluster. And on the bottom are 5 self-managed clusters. I don't know about you, but to me, this looks like a skyscraper. OK. Let's take a look at how everything looks on screen. So I have split my screen here in two, just so I can show you our management cluster. I will wow, this is really slow. I just want to show you that things are actually running here. I'm also going to show you at what scale we're running our core services. And let me zoom this out a little bit. So you can say some instances have 1,000, some 500 instances. Now, we have modified the Kubernetes dashboard, so we can also visually show you what the scale looks like. So we've added this graph tab to the Kubernetes dashboard, and that is the visual representation of what we just saw. That's only the master cluster. I will zoom into this area here. So each of the triangles in this chart is a service, and each of the dots are pods from that service that are running in the cluster. Let's take a look at the worker clusters. So here I have, let me show you this. We'll use a very nifty tool called kubectx. Lets you easily show what are the Kubernetes contexts that you're looking at. So on the left, you'll see each of these sessions pointing to one of the GKE clusters, 1 through 5. And on the right, we have 5 self-managed Kubernetes contexts. So I'm going to show you what's running in these clusters by watching the command kubectl get pods. And what's running is absolutely nothing. But that's a good thing because we can't visualize it yet. So if we were to use that Kubernetes dashboard and wanted to visualize a low workload that is running in 10 Kubernetes clusters, what are we going to do? Install it in each one of the clusters and then have 10 screens up? Then what if we had 100 Kubernetes clusters? That doesn't scale. So we've built a custom UI that aggregates all the information from the clusters and displays it in a single user interface. Right now, I'm just going to show you the one cluster we have running pods. That's the master cluster. Let me pull the dots together a little bit and slow down and make them bigger. So these are the service pods that we have running in the master cluster. We're going to see what's running on here. OK. We're going to use Docker Compose to simulate these 10 different users, each of them using a different data file of 20 variables each, to submit to the guided build API, 120 models. So let me see what this will remind you of. It's colorful, isn't it? Isn't it funny how things in the real world remind us of things that scale in the virtual world? So here is the workload of these jobs that we submitted being distributed between all of the Kubernetes clusters. And let's take a look at our rainbow here. Well, as it happens, the demo gods are not always in favor of us. But that is why we have screenshots. You can see the workload here much better anyway. And this is what these 1,200 models look like when they got created in all the 10 Kubernetes clusters. So I once saw a demonstration of somebody building a lot of containers and running a lot of containers in a cluster. And that visualization was beautiful. And it honestly looked to me like a galaxy. So when I saw this one for the first time at scale, I thought that each one of these little clusters looks like a galaxy. So I made a comment to my team. Guys, I think we've inadvertently modeled the universe. If you want to see this demo at bigger scale, 10x and 100x, I invite you, after this talk, to move to the next hallway, room 11, where you'll be able to see this running at much larger scale. So let me see if we can. I'm going to stop it, and we'll see. This is. Yeah. Things are being created, but yeah, it's beautiful, isn't it? The ocean of data that Fabio talked about is real. And being able to extract that answer, what is the best model, what is the meaningful information in this ocean of data, is actually not very straightforward. But that is the reason why we did all of this. So let me run a query here. So we can get, yeah. We can get our answer. The answer will come up once all the metrics get accumulated and ranked. Because we started with a completely blank system, we don't have the answer yet. However, what I wanted to point out is that, as in many things in science, the answer to the question, what is the best model, is it depends. If you use the criteria of root mean square error, then the answer is 1. If you use max percentage error, then you might get a different model, or average percentage error. I do want to leave you with a few things to take home. First of all, real-world use cases require scale. We demonstrated orchestration and analytics. We showed you screenshots of scale. We used Docker, Kubernetes, Tensorflow, and Kubeflow on scalable infrastructure and managed services from Google Cloud. I also want to leave you with something that I'd like you to remember this talk by. A year, 2 years from now, when you think back about Fabio and Alex from BHE that talked about orchestrating of containers and scaling things up, this is the one talk where you saw how to use skyscrapers and rainbows to model the galaxy. I would like to read out some names here. On this slide, we have a small thank you for some big names. Arun, Andre, Renato, Shurya, Christian, Imran, Murli, Mahadevan, Simon, Trang, Rahid, Alex, Kelsey, Sina, Young, Ning, Tad, Josh, Scott, Will, and many more. Thank you for collaborating and encouraging us. We have a page full of references for you. Anyone who would like to read more and who has doubts about what we're showing here today, please refer to these links. And you can always get in touch with Fabio and I offline. But if you have any questions that you would like to ask us now, please pick up a mic and we'll do the best we can to answer. Thank you.
Thank you.
A network connectivity issue prevented the demonstration in this session from working flawlessly. The issue was mitigated immediately after the presentation. In order to provide you the full experience of this amazing capability, we have recorded the following additional video.